Great. Now we have Simcha, who's going to tell us about the backwards compatible row-based exceptions in ML.
All right, thank you. So I want to start with looking at type safety in the presence of exceptions. So normally type safety says that type programs cannot go wrong. But in the case of exceptions, it's a little bit more subtle. For example, we have the following program, which maps over a list of integers and always raises an exception. And then its type says that it is a list of integers, but there's no information in this type displaying the fact that this program raises an exception. So instead, in the presence of exceptions, what we're interested in is exception safety, which says that type programs cannot go wrong and also do not raise exceptions. Well, this is a property that you want for your whole program, but you definitely don't want it for individual components of your program, because, for example, the program here should definitely be type checkable as long as at some point the programmer handles the exception, and then in the end we know that the complete program does not raise any exceptions. So what people do to accommodate that is they make use of these rows to track exceptions. So we say that not only the program above has type list of integers, but it also has a row containing the singleton label error, indicating that the exceptions with the label error may be thrown. And then we say that a type program at an empty row cannot go wrong and also does not raise exceptions. So this has been done before. What we are interested in is designing a type system with this exception tracking, which is also backwards compatible. And with backwards compatible, we mean the following two things. First, we want programmers to be able to opt out from this exception tracking, and function signatures should be able to migrate it to this exception tracking one at a time. So the first point means that if a programmer has written an ML program and they now decide to switch to our type system with the exception tracking, then their program should remain to type check without any additional work for them. Second, let's say if a programmer has the following two programs where the first program is used in the definition of the second program. Now, what the programmer can do is generalize the type of the first program by adding exception tracking information. For example, saying that it raises exceptions in row. Then the second program should still remain to type check without the programmer having to do any additional work. So to come to our contributions, we have an ML-style type system with support for a bunch of regular ML features such as higher order references, polymorphism, concurrency. We also support local exceptions, which means that in ML, exceptions can be declared locally, for example, in the function scope, instead of what you have in other languages like Java, where you statically declare the exceptions which can occur in your programs. And of course, we have exception tracking. And we do this in a backwards compatible way, as we said before. And then we have safety and abstraction guarantees. So we have the exception safety statement from the first slide. And we formalize this all using binary logical relations via a relational separation logic, which has support for these local exceptions. And we mechanize this all in ROC using Iris. So in this talk, I'll mainly be focusing on the parts highlighted here in orange. So first, let's take a look at these row-based exceptions. So as said, we track these exception names via rows. So we either can have the singleton row, we have row variables which we use for row polymorphism. We have a, the first one is of course the empty row. The third one is the singleton row, which says that an exception with label E can be thrown, and then we can concatenate these rows. And then we annotate the typing judgment with these rows to indicate that the program E does not only indicate that it has type tau, but it also may raise any exceptions in row. And similarly, we annotate the function type to indicate that the function can throw any exceptions in row. And we also annotate the accent type, which is used to make exceptions, first-class data in ML. And then row polymorphism gives us stronger types to track these exceptions. So for example, we can have the following type for map, which says that if we have a function which may throw any exceptions in tau, then if we map this function over a list of alpha, then the output may also throw any exceptions in tau. Now this has been done before. What we have done is make this backwards compatible by adding a top row, which indicates that any exception in scope may be raised by the program. And this you can see as basically the default behavior you've got in ML. There you don't know anything about the exceptions that may be thrown. So we added this to the syntax of the rows. And then we get our backwards compatibility. So recall we wanted to programs to be able to opt out from this exception tracking, and they should be able to migrate their function signatures one at a time. So the first theorem that we've proven is that our type system is an extension of a regular ML-style type system, which does not have this exception tracking. So if you have a typing judgment without any exception tracking, then we can prove that we also can type check this program in our type system at the top row to indicate that we don't know anything about the exceptions that may be raised. And note that we have to translate these types here from the types that we use in the non-exception tracking setting to our exception tracking setting, which we do by annotating both the function types and the accent types with the top row to indicate the default behavior that you've got in ML. And second of all, our type system is designed such that we have the following property, which we call graceful generalization, which says that we can subtype interesting examples one at a time. So we start with a type which does not have any exception tracking, and then we show that via subtyping we can derive a type which does have exception tracking. So this makes the point clear which we had earlier, where we had two programs where the second program used the first program. If we now generalize the type of the first program to have the exception tracking, then we can show that it's a subtype of its original type, then we can still use program 1 in the context of program 2. Well, this is not a formal property, but we show for various interesting examples that we can give such a stronger type and its subtype derivation. And moreover, we can do precise exception tracking via rank and row polymorphism, as we'll see in the following example. So this example is one which we adopted from the Jane Street OCaml library. And it basically allows the programmer to program with a return statement just like you would have in an imperative language. So if we just take a look at the type of this method, we can see that if we want to construct some element of type alpha, then it suffices to only construct a closure which makes this alpha. But while we construct this alpha, we get access to a return function of type alpha to bottom, where this bottom indicates this return function never returns. And it's implemented using these local exceptions. So we start by locally declaring a return exception in the scope of this function. Next, we use this locally declared exception to create the return function. So every time this return function is called, it raises the return exception. We pass this return function to the closure that is given by the user. And then finally, we wrap this in a try with block, which catches any return exception raised by the user. So anytime the user called the return function, the return exception is thrown, it's captured here, and then we can pass on the payload of the return statement. Well, if we want to have more precise exception tracking for this function signature, first what we should do is apply our extension theorem by annotating all our function types with this top row. And next, we want to be more general in the types of exceptions that may be thrown while using this function. So we allow the user to choose a row theta user, which they may want to throw while constructing such an alpha. And we annotate the function types with this to indicate that they are allowed to throw these exceptions. But now this is a problem because in the closure, you can see that the user is only allowed to throw exceptions in theta user, while internally the return function that they have been given makes use of an exception. And the bigger problem here is that the user does not even know which is the label of this exception, because it's only declared in the scope of this with return function. So we circumvent this by providing this exception to the user as a rank 2 quantifier. So the user gets given a row theta local, which is can be seen as the permission to use this return function, and it's given to the user since it's now a rank 2 quantifier. Then the user can now not only throw their user-chosen exceptions in theta user, but they are also allowed to raise any exceptions in theta local. So that basically means that they are allowed to use this return statement. If we then want to type check this function now with this more generalized function signature, we can see that we can now, after allocating this local exception, we can instantiate theta local with the singleton row. And then after the try with block, we can see that only the exceptions from theta local are handled. So we know that f return may throw either exceptions in theta user or in theta local. All those in theta local are now handled, and those in theta user are bubbled up as indicated by the output of this function. And more importantly, what we can do is we can recover its original type, which did not have the precise exception tracking, as a supertype of this more generalized type. By every time we see a quantifier on the right, we introduce it and then later subtype it to the top type. And every time we see a quantifier on the left, we eliminate it by instantiating it with the top row. Finally, we also have representation independence results. So just like local references, we want these local exceptions really to behave locally. So if we locally declare an exception E, and then we execute F, wrap it in a try with block where we catch all those exceptions in E, this should be contextually equivalent to just executing F, because E should not be in scope of F. Note that this is pretty similar to how local references are should be local if we compare to this more well-known contextual equivalence, which says that if we create a local reference and then execute F and then load R afterwards, then this should be contextually equivalent to just executing F and then returning 10 at the end. In the paper, we present a methodology to prove these contextual equivalences, which we do by providing which is based on a binary logical relations model. And the novelty here is how to semantically interpret these rows, where we have to make sure that the top row is not any exception which may be thrown, but precisely those exceptions which are in scope. And using this methodology, we can prove a bunch of examples. For example, we can show that implementations of a monadic map function, which uses a the with return example from previous slide, or the option monad, that these are contextually equivalent. And in the paper, we have also many more examples involving other ML features, such as concurrency, storing exceptions, and a bunch of other. And then again, this backwards compatibility gives us strong results. So if we can prove a a contextual equivalence at some strong exception tracking type, then by subtyping we get also that this contextual equivalence holds at the weaker non-exception tracking type. So to conclude, we have a type system for exception tracking in ML-style languages, and we use row polymorphism, this stop row, and subtyping to ensure backwards compatibility. We have safety and abstraction guarantees, and we have all proven this correct in ROC using Iris. So that was all I had to say for now. Thank you.
Thank you very much. We will now take questions for the speaker. Yes.
Do you have any plans to extend it to beyond exceptions to like arbitrary effect handlers?
Ooh, we did think about it. We did think about it. I think it seems like it's mostly or that you have to combine a lot of interesting features, which makes it hard. Another problem which we thought about was that currently how we prove this all correct is using this binary logical relation model, and in this setting with exceptions this is relatively easy, but once you go to effect handlers things become way more complicated. So we're unsure how scalable this is.
Thank you.
Yes.
Hi there, I'm Dan. Thank you for the nice talk. I was a little, maybe you can say something about type inference, because I was a little surprised you had the catenation on rows, and usually people use only like tail polymorphic rows, because that's easier for type inference. I don't know if you've thought about this, or?
Yeah, so the type system is purely deductive, so we don't have any inference yet. We already thought about, we already encountered other issues, I guess, with type inference, because our type system relies on this subtyping, and this already becomes a problem as well. But we haven't really thought that much about the syntax of our rows also because of
thanks.
that.
All right, let's thank the speaker again.